This is Physics 30, Chapter 1, Lesson 5. Today we're talking about acceleration vectors. So we've previously covered displacement vectors, we've talked about velocity vectors, and now we're going to cover acceleration vectors. We already know that acceleration is the change in velocity over change in time, and we can further define change in velocity as final velocity minus initial velocity. Looking at an example, if a car is traveling at 30 meters per second north and makes a gradual left turn and eventually heads 30 meters per second west, if the turn takes 20 seconds, what is the average acceleration? Now, initial thought might be, well, it's traveling 30 meters per second at first, and it ends up also traveling 30 meters per second at the end, so therefore there's no acceleration, there's no change in speed. And it's correct to say that there's no change in speed. However, that does not mean that there's no acceleration, because acceleration doesn't deal with speed, it deals with velocity. And the key thing with velocity is that it includes direction. So while there's no overall change in speed, there is a change in acceleration because there's a change in velocity, because there's a change in direction. So looking at this, we can say acceleration is the change in velocity over change in time. And we know our change in velocity will be final velocity minus initial velocity. So the final velocity is 30 meters per second west. That's what ends up happening at the end of the scenario. And we can subtract the opening 30 meters per second north. So we've got 30 meters per second west, and we're subtracting 30 meters per second north, which really means that we're adding 30 meters per second south. Then that gives us this red resulting vector. And we can solve this with Pythagoras, plugging everything in. We'll find that the resulting vector is 42.4 meters per second. Then we just need to again find that angle, and we can quite easily see that this is a 45-degree triangle, or you could use inverse tan 30 over 30, and you'll get 45 degrees. Using these two things together with the resulting vector of 42.4 meters per second and the angle of 45 degrees, we can go back to acceleration as change in velocity over change in time. Our change in velocity is 42.4 meters per second, and we were told previously that the time was 20 seconds. So then we can calculate the acceleration to be 2.1 meters per second squared. So the overall acceleration is 2.1 meters per second squared, west 45 degrees south. At this point, it's a good thing to remember the law of sine and the law of cosine. Law of sine says A over sine A will be equal to B over sine B equal to C over sine C. And the law of cosine, C squared equals A squared plus B squared minus 2AB cosine C. These are things that you would have learned previously in a different math course, and there are things in the physics course that are just assumed that you will know and know when to apply. So just want to remind you of these concepts in case you need to employ them at some point in this chapter. An example, a stone skips off the water as shown. Find the acceleration if the skip took 0.02 seconds. We're going to solve this question in two different ways. One, we're going to solve it using the cosine law, and the other one we'll do afterwards using x and y components. You can use either method, both are equally valid. They might give you slightly different numbers, off by a decimal or two, but they should be very, very close. The thing with the cosine law is it really only works with adding two vectors efficiently. The x and y components, although it's kind of a lengthy process, you can use it with any number of vectors. So personally, I would only use the x and y components, but we'll also go through the cosine law here in case you want to use that instead. Either method is fine. So again, for acceleration, we need to know the change in velocity. Velocity final minus velocity initial. We can represent this with vectors as such, drawing the final vector first and then subtracting the initial vector. So we could read that as 15 meters per second right 20 degrees up, which is the last vector, minus the first vector, which is 20 meters per second right 25 degrees down. Drawing these two together, remembering that to subtract a vector, we reverse it and add it instead. So here we've got the final vector, and then we're adding on top of that the initial vector. Putting in some key points here for reference, and we end up with this red resulting vector. Now, this is actually a special case where you could use Pythagoras because this did actually end up being a right angle triangle. But we'll still go through cosine law because it's a general case that applies to all triangles, and maybe we can also pretend that you didn't notice this was a right angle triangle. So plugging everything in, we've got c squared equals 15 squared plus 20 squared minus 2 times 15 times 20 times the cosine of 40. Now, when we say c squared here, we're thinking about a side c, and the side that we're looking for is the red vector. So we can label the sides 20 meters and 15 meters as either A or B. It makes no difference. But the important thing is that this side C is opposite the angle we're working with, which would be here. And since we can see the top angle is 25 and the bottom angle is 20, the total angle within this triangle would be 45 degrees, which is what we have here in our cosine. So solving all of that, we get C is equal to 14.2 meters per second. Then we need to find this resulting angle. Remember, the angle we're actually interested in is the angle that forms from our starting position to the ending position. So here we could use the law of sine. Sine 45, because we know this angle is 45 degrees, over its matching side, which is 14.2, is equal to the sine of the angle we're looking for divided by its side, which is 20 meters. And that will give us an angle of 84.8 degrees. Continuing with this, so we can then say that the direction from the start here is going to be that 84.8 degrees, which is this angle, plus the 20 degrees we already had down here. So the total from this horizontal up to the red vector is 104.8 degrees. Now, thinking about the vertical here, the one that would be at 90 degrees, if we take this 104.8 degrees and subtract 90, we will get the missing portion in here, which is 14.8 degrees. So measured from straight vertical, measured from up, the red resulting vector is 14.8 degrees over to the left. So going back to our original definition, the change in velocity we calculated as 14.2 meters per second, and we know already from the question that the change in time is 0.02 seconds. Therefore, we can say the acceleration is 710 meters per second squared, and from the angle we just talked about previously, it is measured up 14.8 degrees left. And that will be our final conclusion. We're going to look at the same example once more, but this time solving it using x and y components instead of the cosine law. Some of you may prefer this method, and personally I prefer this method over the cosine law. So again, velocity final minus initial, same vectors. To add them, we have to reverse that last vector, and we end up with this 15 meters per second, right 20 degrees up, plus 20 meters per second, left 25 degrees up, which we could represent with this equation. So drawing these two vectors, our first vector is 15 meters per second measured at 20 degrees up, and our second vector is 20 meters per second measured at 25 degrees up. Looking for the x and y components in both of these, recalling from our previous video that x is always the vector cosine the angle, we can say x is 14.1, and recalling that y will be the vector sine the angle, we can say it's 15 sine 20, so y will be 15.1. Doing the same thing for the second vector, x is 20 cosine 25, and that'll be 18.1. Now, you might notice that I've put x in here as negative 18.1. The calculator will only tell you 18.1, but we know that it's negative because it's moving to the left, right? From the starting position here, the x value is moving left, so it has to be negative. The y value is moving up, so it will still be positive. And y would be the vector sine the angle, and so y is going to be 8.5. Now that we have the x's and y's for both of our vectors, or if you were doing this in a larger, more complicated example and you had multiple vectors, once you have the x and y values for all your vectors, you can simply add them together. So for x, it's 14.1 plus the other one, which is a negative, so subtracting 18.1, we get x is negative 4, and adding our y's together, we get y is 13.6. So we'll keep track of those values. Drawing in our resulting vector. X is negative 4, so that means it's moving left. Y is positive 13.6, so it's moving up, giving us this red resulting vector. Again, we can solve this with Pythagoras, and we'll get that the resulting vector, our final vector, is 14.2. Using inverse tan, we can calculate the angle to be 73.6 degrees. And so going back to our acceleration equation, it's change in velocity over change in time. So we just calculated change in velocity to be 14.2. And we know again from the question that the time is 0.02 seconds. So solving that, we can say acceleration is 710 meters per second squared, measured left 73.6 degrees up. If you compare this to the previous answer, you'll see that the magnitude of the acceleration is the same, but the angle is measured differently. And that's simply because in this example, we measured it left going up, and in the other example, we said up going left. But if you draw those two vectors, they are coterminal. They result in the same arrow. So they are equivalent answers. So again, you can use either method, whichever one you prefer, either the cosine law or the x and y components. Personally, I find x and y a little bit easier to work with, but if you like cosine law, by all means, it's just as valid. For some practice questions, we're going to work on page 35, numbers 8 to 10.